which class. You can tell which class this new testing example belongs to, given the two boundary you learned from the training data. So you have to find some way to assign some preference over the two boundary you learned in the training set, so that you can make a generalization. And there's also evidence showing that inductive bias exists in the brain. Sure, people are familiar with these dragon illusions. So for example, this is a classic visual illusions, essentially showing that this is an ambiguous pictures, and then the dragon face is actually hollow, but then you see a convex face. And the Bayesian has an explanation for this, and then it relies on the inductive bias people have when viewing the face. So essentially, you can model this phenomena by saying people have an inductive bias for convex face. So convex face has a higher probability of appearing in everyday life than concave face. And then because these images are so ambiguous, so the likelihood are not telling us too much information. So that's our perception, which relies on this posterior, will be mostly influenced by our inductive bias, which in this case will just give us a convex face perceptions. And similarly, lots of visual illusion has been explained in these ways. And then there are other inductive bias recorded. So the one we just mentioned is this convex face are more common than concave ones. And also some illustration built on this inductive bias of light usually comes from above, and the slow speeds are more common, and many more. So the takeaway message from this practice, so we can see visual illusions are not just bugs in the systems. So they may represent something interesting in the inference machine trying to do the right things. And the wrong percepts can often be tracked back to a prior. So this is, but then later on we'll explain how but then in the judgment decision making literature, we know lots of bias are incoherent bias, and we will return to this later on, saying we have a different kind of prior, so that can explain why behavior are incoherent. And after all, the Bayesian inference is really the principled way to provide a solution to this problem of limited data. Essentially by formalizing inductive bias as a prior. But then we also know exact Bayesian inference is computationally intractable for virtually all cognitive tasks. And even in case when it can be tractable, it will probably be wasteful to do the exact Bayesian inference, because we can get a very good estimate, assuming a sampling-based approximation. A good estimate can be obtained by just a few number of samples. So that leads to the model or the rational process model we try to propose here is essentially an algorithm in response to the twin computational challenges. And it has three components. It has a prior just to formalize the inductive bias. And we also assume people arrive posterior, but then this posterior is intractable. And then there is some posterior sampling strategy used to approximate that exact posterior. And we also introduce a optional stopping rule to terminate this posterior sampling process. And we seek to apply these ideas in cognitive and behavioral science basically try to explain bias and variabilities in lots of behavior, including the probability judgment. And we can also explain many other effects. For example, the confident judgments and response and the choice accuracy effects. Hopefully we have time to touch on this later on. But essentially, the variability of the behavior will come from this sampling-based approximation process. Is essentially a computational noise. The bias will come from two sources. The bias will come from the usage of prior knowledge. Is it in this prior? And it will also come from the starting point of these sampling algorithms, and that would also bias the behavior. And these are essentially two sources of bias. And just to make the concept more concrete, so this is what we envision. So we're thinking there is some sort of internal probabilistic model in the brain. And then when people are presented with external sensory stimuli, they form, so combined with this internal generative model, they reach a posterior probability distribution of the hypothesis. And we just draw a sample from this posterior distribution. We call it hypothesis samples. And then these hypothesis sample can be used to form behaviors when people are asked about questions. And then you can just turn, basically, you can just turn aspects of these hypothesis samples to corresponding behaviors. And we see this framework very general, and it's not bounded to, it's not limited to any specific task. So in this case, can be explained, for example, can be even used to explain some behavior recorded in intuitive physics literature. And so in this case, the hypothesis, the stimuli was showing the initial movement of two balls shooting out of this cannon. So we have essentially some initial motion of these two balls, and the hypothesis space, so that's the stimuli. And the hypothesis space, the hypothesis will be the future trajectory of these two balls. And you can ask all sorts of questions about, for example, you can ask people whether the two balls will collide in the air, or whether the two balls will, well, you can ask all sorts of questions about these stimuli. And the main takeaway is that the hypothesis samples should provide sufficient statistic for a wide range of behavior output. So you can ask people to make a judgment, and then you can ask people to make probability estimate based on these sensory stimuli. Lots of things you can ask, but then we're saying these samples are sufficient to support a wide range of behavior output. And here is a complete algorithmic implementation of these models. And so coming back to these numerosity examples, we have a 25 dots briefly appear on screen. And then internally, and this is this could be a type of posterior of hypothesis. And in this case, we just assume a simple Gaussian distribution. And this hypothesis space is on the number of dots. So it could be a Gaussian distribution with the mean at 24. And then you have some standard deviation around the mean, just to represent some sort of uncertainty that could arise from the sensory stimuli, or could also arise from the internal information processing. And although in this case it's a simple Gaussian, but in lots of other conditions it will be way complex distribution. So approximation is needed. And then in this case, we just show a five samples shown from this posterior. And we're assuming that this sample was generated by some local sampling algorithm. And one of the, so for example, MCMC type of sampling algorithms. So one of a byproduct of this MCMC type of algorithm is that the samplers will be autocorrelated. So there's some degree of dependency between the samples. Just to illustrate, we just show 5 samples were drawn, for example. So 26, so sequentially, 26, 24, 27, 22, and 23. And when it comes to make an estimate, we just assume that last samples use as the estimate. You could use mean, the average of these 5 samples as the estimate, but then given the fact that these samplers are autocorrelated, it might be wiser to use the last samples, although there are other considerations there. But here we just use this using the last sample as their estimate. For in this case, 23 is reported as the estimate, and then these when people ask to produce some confidence intervals, we can essentially just transfer the empirical quantiles of these samples as the confidence intervals. So if people ask 60% confidence intervals, we just strip off the two two extreme samples, and then make our confidence interval as 23 and 20, between 23 and 26. And then in case there are more granular confidence interval was queried, then some linear interpolation could be assumed. And this is essentially a similar idea from Peter Usling's naive statistician model. Then when it comes to probability judgment, we just, and probability judgment is, well, maybe we talk about decision-making first. And decision-making questions can be asked, for example, in this case, a decision about whether the number of dots appear on screen is greater or less than 25. So there should be a boundary here at 25 that basically partitions the hypothesis space into 2. And you can see the red and blue space, 2 subspace, each supports one of the options. So the red space supports less than 25 dots. Blue space supports greater or equal than 25 dots. And then we just, essentially we just transfer all these hypothesis samples into evidence that supports each choice. So I've basically color-coded all the samples. All the blue samples are supporting choice B, and all the red samples are supporting choice A. And they're going through this evidence accumulation process with a study so this is an evidence accumulation process, but it's also a Bayesian inference process. As you can see here, we are assuming people have some prior belief on what could be the correct answers, correct choice here. So here, assume a bias prior. So this is a beta 2-1 prior. And then we are assuming some optional stopping rule here with this is essentially a max minus next heuristic stopping rule. And we can also do some optimal stopping, but then they are qualitatively similar. So here, the threshold is 2, which means whenever we have 2 more samples supporting the either side, we terminate the sampling process. And you can see here the trajectory of accumulation process. And then in the end, we got beta 5.3 as the posterior of the evidence. And then that's when the process got terminated. And then choice is very obviously the observing boundary, which is represent the choice. And then in this case, the threshold of choice A was breached. So choice A will be illicit. And then the response time would just be some sort of noisy version of the number of samples. And in this case, we just assume there are some Erlang distribution, and then the number of samples is just 5. And the confidence readout, interestingly, is just we didn't assume any loss. So in the end, we got a beta 5.3 as our posterior, and we just assume the confidence judgment to be the mean of these posterior. And in this case, and for the beta distribution, the mean of the beta distribution is just the parameter divided by the sum of the parameters, which is 5/8. And these are similarly, we could apply that to a probability judgment. If we're assuming a similar prior of beta 2.1, then a probability judgment will be reached at 5/8. And just to contrast this whole framework with a classical framework, we have this a sequential probability ratio test. And for them, they also start from for example, the same sensory stimulus. But then for the SPRT, it's essentially sequentially recalling a noisy version of the sensory stimuli, as we can see here. And then it just calculate the log likelihood ratio between the two choice against this noisy percept. And then the process, so you keep adding the log likelihood ratios, and then until some threshold, you terminate this process. And you can also record the choice, response time, and the confidence. But then, because these hypothesis, the hypothesis space for this is essentially binary. You only have you either you either have a choice A or choice B. So for this one, so for example, these 3 behavior output are not supported by this less granular hypothesis space. So this is essentially the whole framework. And I think Jake will be next talking about how we apply this framework in explaining some psychological data.
Sure. Let me just share my screen. Hopefully you can see my slides okay. Yes, so yeah, I'm going to be following on from what Zhu was speaking about, I'm going to be taking that broad framework and trying to narrow it down to a specific application. So one of the benefits of ABS is it can do lots of things, and there's a lot of things we don't have time to go into, unfortunately. But we're going to be focusing on one particular application that we've run to test the implication of this. So one of the strengths of ABS is because the samples that you retrieve from the posterior are able to be coded according to different responses. Essentially, they contain enough information to answer multiple queries. We might be able to predict some relationships between different responses. And so this is something you can see in the connection between decisions and reaction times. But here we're going to be focusing on the connection between decisions and estimates from the same set of samples. And this connects to a couple of effects that have been observed in previous research, which named anchoring and repulsion. So a lot of people here might already be familiar with anchoring. Certainly, this is one of the kind of classic Tversky and Kahneman biases, where people's estimates of something tend to be pulled towards values that they see beforehand. So in their initial demonstration, people were asked to estimate the percentage of African countries in the UN. But first they span a roulette wheel, and the roulette wheel either gave them a high number or a low number. And people's estimates were lower following the low comparison than the high comparison. So people are kind of pulled towards these values. And that's been replicated quite a lot in the last 50 years. And then more recently, we have a repulsion bias, which is kind of similar to anchoring, but runs in a different direction. So in repulsion, this is something that's been observed in perceptual tasks, where you will give people a perceptual stimulus and ask them to estimate some part of it. So it might be direction of motion in a series of moving dots. And they'll then, beforehand, they can give them a comparison that says, is it left or right of this boundary? And in this case, you actually see people biased away from the boundary. So people sort of avoid answering nearby the boundary. So it's kind of the same paradigm, but giving an opposite effect. But interestingly, both of these reflect cases where the decisions and the estimates appear to be related. In fact, the decisions appear to be biasing the estimates away from the true values. So maybe there is some connection between these responses, and that might be something that ABS can get access to. So we return to the example that Zhu was giving in the previous section. We have some sort of stimulus centered on 24, and we have this decision boundary between 25 and 26. We can produce both a decision and an estimate from the same set of samples from this data and see what kind of effects we have. And we will see both of these effects because of the autocorrelated sampling algorithm and also the optional stopping rule that Zhu was describing previously. So first, we have to assume that the sampler begins at this boundary, so this midpoint between 25 and 26, and then it's autocorrelated, so it means it suggests new samples close by to previous samples. So we can use a basic sort of MCMC Metropolis Hastings process to decide whether you accept or reject samples. And each sample, we can pass that to this kind of evidence accumulation process. And as you gain more and more evidence, you'll shift further and further towards one of the boundaries. And eventually, once you cross that boundary, that is your decision. But then crucially, you can reuse those samples. So rather than worrying about the color of them, now we're worrying about the actual number. And then you can take an estimate from that, as we were talking about previously. So the same set of samples being reused for both things leads to a connection between those responses. And because the optional stopping rule means that the sampling will only stop where the evidence favors one side of the boundary, it won't stop where there's ambiguous evidence. We will see repulsion away from the boundary. So it'll stop where there's evidence away from the boundary, and that should give us a repulsion effect. But similarly, this autocorrelated sampling algorithm beginning at the boundary means that if you have a limited number of samples, you might not be able to get too far from the boundary, so we might see anchoring. So we have both effects emerging from these things in different directions, but the way you can separate those is by considering them according to how far the target is from the boundary. And what we see from ABS is that ABS will be pulled towards distant values because starting further from the target, you can't move as close to it. So that's anchoring. But at the same time, if you're nearby to the boundary, you're going to be more focused on continuing to sample until you get credible evidence that one alternative is more likely than the other. So we can simulate that out by taking, so in this case, H star is our particular decision boundary, and we can compare that to various different target stimulus values. So the true values are on the x-axis, and then we have the estimate along the y-axis, and these heat map is essentially the distribution that is produced by the ABS. And what you can see is at the far edges, we see estimates being pulled up from the blue calibration line at the lower end, and then at the upper end, we have the reverse. And again, that's anchoring because the estimate's being pulled towards this H star point. But at the same time, at the center, these nearby values seem to be pushed away from answers nearby to that boundary. So it is achieving both things purely according to how far the target is from the boundary. And this is something that it means that there's two kind of key aspects that this predicts. First is that this means that we might see both effects in the same task based purely on how far the target is from the boundary. And we might also see that these things aren't necessarily domain specific, even though a lot of the existing evidence has been limited to one or the other domain. So repulsion has generally been observed in perceptual tasks and anchoring and cognitive tasks. Maybe we can see a crossover here. And so in a recent paper, we compared these ideas. We tested these empirically in both perceptual and cognitive domains to see if this kind of prediction was correct. And so we have a paper that's currently awaiting publication at Psych Science on this. Hopefully that'll be available soon, but in the meantime, I'll try and describe it as best I can briefly. So we used a basic decision estimate task where we gave people stimuli and then either first asked them to compare them against a particular boundary and then ask them for an estimate. So in this case, it is a basic numerosity task. We flashed a set of dots very briefly on the screen. We asked them whether it was above or below. So the little line on the semicircle here is the decision boundary. We asked them whether it was lower or higher than that line, and this range is 0 to 100. And then once they made the decision, they picked a point on this arc between those extremes that was their estimate. And we use a continuous response scale to avoid any kind of rounding that we might see if people just typed numbers. And so in order to get that distinction between nearby and distant boundaries, we used a bimodal distribution for stimulus values, although participants weren't aware of this. They just, all they were told is that values would be between 0 and 100. And so that means we have this low region between 20 and 30 and this high region between 70 and 80. And then we have these two boundaries at the middle of those ranges, so we can contrast nearby boundaries in both high and low cases and distant boundaries. So that achieves both things simultaneously. And then we ran this as an online experiment last year. And the brief thing is that we didn't include estimates in every trial, just so they didn't anticipate the estimates. So that was a very brief run through the method. I hope that was clear enough. So we'll just jump straight to the results. So these are the aggregate distributions for the responses given by our participants in each of these four cases. So this is where we have low stimulus values against the nearby target. And this is the contrast where you have high stimulus values against a high target. And what you can see is, firstly, and we can look at the empirical test at the same time, the estimates tend to be drawn towards these distant boundaries. So this distribution is shifted slightly closer to this dotted line here and same here. But at the same time, and yet that is significant according to these tests. So there's significant evidence about anchoring. But at the same time, there appears to be these divots in these respective distributions that suggest people were avoiding answering nearby to the boundary. We assess this using something called Eigen-Stipp test, which essentially looks for these gaps in the distribution. And we see significant evidence of a dip in this upper left panel here, but not so reliable evidence here, despite what it visually looks like. It might be that this tail is not quite convincing evidence. And this might be something to do with an asymmetry between low values and high values. So we have pretty decent evidence in the perceptual task of both anchoring and some repulsion, although there's some asymmetry. But to kind of give us the counterpoint, we also run the same design in a cognitive experiment, and it basically takes the same principles, and instead of the stimulus being a set of dots that briefly appeared on screen, we ask these questions about ages that people did things. We've tried to match something that would have the same 0 to 100 scale approximately. And again, we selected questions to have a kind of bimodal, half of them were low, half of them were high kind of structure. And then some more minor things because you can't briefly flash these questions, and we didn't repeat the questions because people have already answered them once, they might recognize them again. So again, yeah, a very brief introduction, but returning to the same results that we saw previously. So again, we see some evidence, good evidence that estimates are drawn towards these distant boundaries, a little bit weaker than the previous experiment, but still significant. And then again, we have visual evidence of these divots, but once again, it only returns significant in this Hardigan test for this upper left panel. This again isn't reliable. It might be because there's so much more mass of the distribution on this side of the boundary. And then we can compare that directly against a model simulation from the autocorrelated Bayesian sampler of this task for a more direct comparison. So we do see anchoring and repulsion in these simulations. Admittedly, the anchoring is much stronger than we see in the empirical data, and the repulsion is possibly weaker. But this is a very basic simulation with some hand-picked parameters, and this might be something we can improve if we did some more fine parameter tuning, or indeed if we looked at other ways of selecting estimates from the collection of samples, which Julie touched on briefly earlier. So that's a very quick run through of this project. Hopefully that was enough to give you some idea of what this was talking about. But to briefly summarize, what we were looking at here was this concept that the autocorrelated Bayesian sampler has this connection between multiple responses from the same set of data, and that allows us to predict both anchoring and repulsion effects. And we see that emerging from the specific elements of our autocorrelated Bayesian sampler. So anchoring coming from the autocorrelations and repulsion coming from this optional stopping. And we've seen that verified in some empirical data. So what this might suggest is taking this idea from the ABS is that these aren't phenomena that are explained by distinct processes. These are coming from a kind of single rational process that's applied across multiple queries. That's the takeaway we'd hope to suggest from this. So that's a very quick rundown of this one project. There are, of course, many other aspects of the ABS that we don't have time to go into, but I think what we'll do now is we'll hand over to Adam, who will talk about some of the other elements of sampling, the other projects we've run recently, and briefly run down through some of those.
Thanks, Jake.
Just a quick reminder, we have about, I think, 3 to 5 minutes, and then we will move to the question section.
Okay, great. I'll try to be quick then. So yeah, I mean, I think Jake and Zoo did a great job of trying to outline the overall modeling approach and one application to try to explain, the sort of biases that people generally study, things like anchoring effects and how decisions and estimates interact. So that's kind of like one thrust of what we were trying to do with this project. But another one is trying to get at like, what is the engine that drives this? So all these, the ABS model is based on the idea that you have some sort of sampling algorithm that's generating samples, and then you convert it into choices or response times or probability judgments. The kind of a big question that we have is, what is that sampling algorithm, if there is one, that would explain how what things come to mind and how they're translated, later into these different measurements you can make of people's behavior. So in order to get at that, it doesn't make much sense to look at the decisions people make, because that's, we would assume, is like an aggregate of a bunch of samples. It's really hard to figure out what the algorithm is that underlies that. So instead, we've been focusing on looking at time series of people's data. And we've been looking at things like having people name animals that come to mind, or this really kind of boring task where we have people sitting in a booth for 20 minutes and press a button every time they think a second has passed. So we can generate like a long time series of human behavior, and then we can look at sort of statistical facts about these time series and see if they match the sort of statistical facts that these algorithms produce. And this is something that Zoo has been doing for a while. He's sort of pushed this poor subjects to do this task where they sat in the booth for 20 minutes hitting the button every second. And you find lots of interesting things, like first of all, that people make lots of sort of like small changes in the estimates that they make. So they'll say something like a second for a little while, and then occasionally they'll make like a big change in the estimate that they make, and then they'll stick to that area for a little while. And also not just that there's big and small changes, sort of like this quantile plot, so these heavy tails and how people change their estimates, but also they're auto-correlated with each other and very, very strongly. So there's sort of like long range autocorrelations that go across behavior. It doesn't just depend on the last estimate you made, it also depends on estimates from quite a long time ago. And we can look at various algorithms. We can look at things like MCMC, which is like a basic kind of algorithm. And we can look at more sophisticated versions like MCQ, basically runs a bunch of chains at once that kind of help that main chain to sample away from the mode of the distribution. And we can look at things like Hamiltonian Monte Carlo, which is another sort of fancy version that allows you to sort of take the gradient of the distribution you're in to make better proposals than you would otherwise. Looking across all these different algorithms, having these time series allows us to distinguish between these things, and we find sort of evidence for sort of more sophisticated algorithms that might explain people's behavior, like this MC-cubed. So that's just sort of a flavor of what we're doing, and just to say we've kind of applied it to things like numerical prediction, so people trying to predict time series of prices, like you might in a stock market, and we find things like MCMC and MC-cubed do a better job. So this is work that Zoo sort of collected all the empirical data on, and Jake did a lot of modeling on. And then we found that these different algorithms better explain the sort of facts about people's time series than the different models that have been developed for this task, like delta rules or exponential smoothing. And also we've been keen on various things like random generation. So we've been asking people to sort of like imagine putting numbers into a hat and pulling them out one at a time and generating them randomly. And random generation, people don't generate randomly, but they generate in a way that sort of fits these sort of local sampling approaches. So we've been looking at various algorithms to try to explain that as well. So trying all sorts of different kinds of time series to try to identify what could be the thing that's driving these sort of sampling. So I know we basically run out of time, so I want to stop there so that there's, of course, more time for discussion. And yeah, thank you very much.
Thank you, guys. And I appreciate you being fast, allowing more time for questions. So now is the time for questions. Yes, Adam.
Hi, thanks. And thanks very much, all of you. I think that's really interesting and looks potentially really powerful. I guess it's a question that kind of stems a bit from the last stuff that Adam was talking about as well, and maybe I think relates to that. which is, Jake, when you spoke about the model simulations for the data, one thing I was interested in is, what are the parameterizations? So what parameters are required in order to run those models? And so Adam said, there's lots of different sampling approaches. There's obviously quite a lot of work in Zhu's talk as well, but I wonder, what are the parameterizations there? Or what are the parameters that need looking at?
Yeah, so it's a fair question. So those are essentially handpicked parameters. So we didn't do any sort of tuning of them. They were just sort of what kind of works best to hit those results. But so yeah, the parameters are essentially some of the pieces that Zhu was talking about at the start. So you have firstly the sort of the threshold for the accumulator. So how many samples do you want to consider before you make a decision? So how strong you need the evidence to be, and then also the sort of the level of autocorrelation, in a sense, like the step size of the autocorrelation, how far you allow the sampler to drift from trial to trial. I think those are the major ones that I remember immediately. So those are the kind of key aspects. So like how strong the autocorrelation is, how far it can move in any given step, and how much evidence it needs to accumulate. Because obviously the bigger the step size, the less anchoring you'll get, because it can move further. And the more samples it can take, essentially the higher the threshold, it'll gain more samples, but it might be a little bit more ambiguous. So it can collect more samples. And there's a sense there that, like, depending on how you take the final estimate from that collection of samples, you might undermine that a little bit. So if you might take 50 samples, but if you only use the last one, then maybe that doesn't matter. So there's different elements there as well. But yeah, those are the kind of key elements.
Thanks, that's very. Can I ask one quick follow-up, Yefim? Okay. So just, am I right in thinking, therefore, there would have been some parameterizations that would have seen the repulsion effect in that? Because I was sort of quite struck by the fact that you did a study, you expected sort of repulsion and anchoring to go, opposite directions, as it were. So is it a case that there were some parameterizations where you would predict or would give a repulsion effect in that study?
Oh, so I think we do have a repulsion effect. I think, arguably, it's just very small. It's just like I might have to share the screen again, but essentially there's a very small divot, right? The empirical is a lot more pronounced. You have sort of more clear bimodal, whereas in our simulations it's much more close together. But they are not answering. Yeah, the model is not answering on the boundary, so it is a paucity of responses there.
Thank you very much.
Any additional questions?
Can you be maybe a little bit more concrete about how the hypothesis, prior hypothesis, coming from? Are there what the experimenter gives, or specifically in two experiments? Is that the general principle for hypothesis, or there are also?
Yeah, I think there are, in general, we see this. So for example, these are just, for example, in the animal naming experiment, the hypothesis would be, the hypothesis will be the semantic space of animal names. And then the hypothesis would be each individual animal names. And then, for example, in the intuitive physics experiment, the hypothesis space typically would be the future trajectory of these objects in for example, this intuitive physics experiment. And then if it's in this social reasoning kind of setting, then the hypothesis space typically could be the hypothesis could be about what's other people's motives or other people's belief in the social reasoning context. So these are really following the tradition of the Bayesian model of cognition, and how they define hypothesis is typically what we define our hypothesis.
I will try to ask you differently, maybe something related. So in all kind of diffusion models, the prior is the starting point, right? Where you start, it's a parameter. So the question here is, the prior, you model it as a free parameter. Sorry.
Yeah, so yeah, definitely. So there are actually two starting points in the autocorrelated Bayesian samplers, and we kind of mix them. So that may be a little bit confusing. So in the accumulator, there's definitely a starting point in the accumulator, and we conceptualize as a prior there. So you have some sort of bias toward one threshold, then that would essentially mean that the decision maker bring in some sort of asymmetric prior. And then we also have a starting point for the sampler. So the sampler is operating in the hypothesis space, and because this starting point matters because the sampler is autocorrelated. So if the sampler is not autocorrelated, then the initial location of the sampler doesn't really matter. But then it is because it's autocorrelation in the sampling process. So the initial location of the sampler also matters. So these are really two starting point in the models.
But how do you choose that starting point of the sampler? Because, for example, for the anchoring to take effect, you have to assume that the starting point is right the boundary that you give them. Why would it be this and not anything else? So your assumption is what makes the anchoring happen, right?
Yeah, I think Jake may have a better answer on this, but then so in general, for the MCMC type of algorithm, you need to give it some starting point. So otherwise you can just start randomly.
So you are estimating the starting point based on the data. This is a free parameter again. So you have two free parameters for the priors, right?
In the anchoring simulation, I think we make the starting point explicitly coupled with the decision boundary.
Okay.
So it's fixed at the decision boundary.
And Jake, maybe and this assumption is what makes anchoring the prediction of anchoring, right? It is this assumption that makes it.
Yeah, so that is true. That so yeah, we wouldn't consider it a free parameter because it is an aspect of the design, but it is that like building in that assumption that is where the sampler starts is what gives you anchoring. I will say that this is partially based on some work by Falk Leader and his colleagues that suggested anchoring can be considered a rational effect if you assume that people start sampling from the decision boundary, and then they have a limited number of samples. So that was the part of our justification for why this model produces anchoring. I guess there is an argument as why would they start at the boundary. I guess I'm not entirely sure what their justification for that is, but I suppose it would be the idea that this is the most sort of relevant value at the time that you begin sampling. So when you're first sampling, the value that is in mind is the boundary that's been presented to you. So that is the kind of initial starting point. But I guess you could relax that. But as you said, then you have to set that starting point somehow else. And where is that going to go?
So I'm not sure if Nick wanted to add something, but
I was going to say, I was just going to say, I mean, of course, we're only assuming that the anchor is somehow intruding on the sampling process. So, I mean, of course, we're setting it in this case to be driving the initial starting point, but it doesn't have to drive it all the time. It could be that sometimes you ignore the anchor and sometimes you don't, so we get the same qualitative effect. So I think the assumption is that, as Jake says, as with Leader and others, we're just assuming that you're being pushed around. Your starting point is being kicked around by the anchor. And that's, if that's not true, of course, then we have no traction. Yeah, and that's the key idea, really. Yeah, to explain anchoring.
Yeah, thanks. So I guess a follow-up would be, so what other like phenomena can the ABS, maybe that you didn't show, can the ABS predict the new stuff that the ABS predicts ABS, right? Yeah.
Can I say something? I mean, you may have a thought on this, and Apple or everyone, but let me say a tiny thing, which is that the way Dew has developed the model is with the classic drift diffusion models as an alternative. So all the things that they do, this model kind of does those as well. But it also does, it can answer questions that they can't answer. So when Ju was talking about the different kinds of questions that you can ask of a Bayesian model, you know, because you've got this sample that you can use in lots of different ways, you can answer all those different questions. So the drift diffusion model is very good at doing things like deciding which boundary has been hit and how long it took. But it's not going to be, it's going to struggle with these more abstract judgments. Or, you know, so it's really a drift diffusion model plus lots of other queries you might make in those sorts of tasks. So the classic sort of random dots tasks, they would be the kind of thing that's in scope, but there are lots of other things as well. Do you want to add to that, Ju? I guess we're almost out of time, but or Adam or Jake.
Yeah, I just have I think we have a preprint out there. Maybe it's worth sending around this preprint, and then in that we have a table of empirical effect that we summarize, and then we also do some lesion on the ABS. And then, so for example, removing the prior or removing the stopping rule, or even removing the autocorrelation in the sampling algorithm, and then see what effect can be predicted or what effect was lost after these lesions. So
and that's on PsycArchive, isn't it, Drew?
Yeah. Maybe it's worth just posting the link in the chat.
Yes.
Thanks.
Yeah, and the general spirit of this is to try to build a model framework which is much more general than the models tend to be in this area. So rather than trying to model a particular one or two sets of data, you're trying to build a framework that could answer all kinds of questions, and you can use it to model all kinds of data. And so it's trying to be broader. It won't be quite competitive with the extremely sophisticated DDM tradition in every particular, but the hope is that it can be broader in scope, more flexible. Unfortunately, I know we're out of time, and I'm going to have to jump off because I have to do a PhD upgrade, which is, the meeting is just coming up as an alert on my computer, I'm afraid. But thanks so much, everybody, for coming along and for your questions and, you know, things for us to think about. But also, please do send us comments, or if you look at the papers and you have criticisms or queries, or can you do this, any of that stuff, that's fantastic. We'd be really grateful to be in dialogue.
Thank you.
Okay, well, thanks for the invite, Yefim.
Thanks.
Sure.
Right,
So
bye.
not only me, it's also Kineret, Orin, and Ido.
Thanks to you all.
Thanks.
I'm going to have to jump right now, unfortunately.
Okay. See you later. Bye.
Okay,
Bye.
guys, this is a good time to end, and unless some of you have some additional questions. So call number 1 for questions. Call number 2. Yes, Ido, go ahead.
No, maybe you guys can, yeah, just a thought. I wonder, to help us people who study simple binary choice task, that if this model is general enough, can you also be used to capture the phenomena that we study, just by repeated decision from
it doesn't
feedback?
have feedback. You know, they don't use tasks with feedback.
I see. Okay, so this is for
sampling. Isn't it kind of feedback?
No, because it's a one-shot task. You need
let them answer.
Okay.
You can think about the sampling paradigm, for example.
To just go, I'll quickly try to do the feedback one. So the kind of prior that Zu was talking about is meant to be responsive to feedback. So that sort of bias you see is kind of a bias toward the response that just got the most recent, you know, that's the good response. So it kind of like shifts you one way, shifts the other way, and that kind of gives you that sort of starting point variability. It's responsive. But yeah, the sort of general question of can you explain it to you know, binary risky choice? That's something we're very interested in. I don't know, Jake has been starting to look at this a little bit. I don't know if you want to say a couple words. It's very, very early, but it's definitely something that we would like to consider in scope for it. But, you know, absolutely, there's a ton of challenging effects to try to explain in that domain.
You know, because our bias was when we decided to go into the simple situation that we felt that much of the cognitive research has so many parameters that unless you're really smart, you don't understand what the model is doing. and I didn't understand it. So I said, let's try to study a situation which we can observe and we don't need to assume parameters. So I wonder if once you do, if you can do that, and that will help us understand it better. It seems it's very impressive, but if it can also do this simple task that we have studied, that will be even more impressive for us.
Yeah, I mean, it's definitely something that we would like to do. The problem with having super complicated models and applied to specific tasks is something that we're also kind of motivated by. So the way we've been trying to approach it is just do more, you know, like rather than just trying to do like one sort of binary decision task, see if you can also do estimates or confidence intervals and see if the same sort of set of parameters can produce qualitative effects across all these different areas.
Yeah, but in our case, you should be able to do quantitative effect, not only qualitative. This is one of the things that's because everything is observable. You know, there are models that can do quantitative prediction and not only qualitative phenomena. So, okay.
Yeah.
But
Yeah,
that will definitely help accumulation of knowledge from our side, if you can help us do that.
Yeah, and the kind of way that we've been doing model fitting is, so the classic way of doing it is to try to find out the likelihood of each response and then trying to find the parameters that explain that. But the way that the model is, you know, has these autocorrelations and all these sorts of things that make the trials non-independent. We've been trying to look for sort of like, not really qualitative measures, but kind of like quantitative indicators of behavior, like how heavy-tailed is the distribution of responses or how autocorrelated is it? And seeing whether we can fit kind of like this basket of statistics at the same time. So it's, you know, we're kind of headed toward that direction of getting quantitative fits, but we don't want to kind of, it's not really possible to like do this sort of trial by trial behavior. You have to kind of look at it sort of halfway between qualitative and quantitative in a way.
Okay. Thanks.
Okay, guys, any final questions? If no, then thank you so much. It was very interesting. It was the first time we had a collaborative talk and you did a great job. So thank you for that. And we hope to see you next time.
Thanks very much for having us and for putting up with our changes of speaker.
Thanks.
Bye. See you.
Bye.